In problem 2 on the quiz that you took last week, you were asked to look at this second order differential equation for the current that you see here, and you were asked to find several things. You were asked to determine what type of damping would be in the expression for that circuit. You were asked to find the transient portion of the expression for the current with respect to time, and ultimately you were asked to find the complete solution for I of t. So the first step here is to convert this second order differential equation into the characteristic equation using a Laplace transform. So everywhere we see the second order derivative we put an s squared, everywhere we see the first order derivative we put an s, and where we see the I itself we just put 1. So that yields s squared plus 5s plus 6 equals 0. Using the quadratic formula and solving, we get negative b, negative 5, plus or minus square root of b squared, so 5 squared 25, minus 4ac, minus 4 times 1 times 6 is minus 24. And so underneath the radical, we're going to get a 1 right there, all over 2a, so 2 times 1. So that yields negative 5 over 2, or negative 2.5, plus or minus 1 over 2, or 0.5. So that gives us solutions to the quadratic of negative 2 and negative 3. So we have non-repeated, distinct, real roots. We don't have any imaginary, we don't have repeated roots, so that means we must be overdamped. So overdamped is the answer to the first part, and the general form of the equation for I of t, the transient portion, is going to be this middle one right here. That's what we're going to put for our expression for being overdamped. So I of t is going to equal a1 e to the s1t plus a2 e to the s2t. Now the last part, we just need to take that general form and look at the conditions that we're given. We're given the initial condition for the current, we're given the initial condition for the derivative of the current, and we're given the steady state condition for the current. And so what we learned in this chapter, hopefully, is that the I of t is going to equal the I at steady state plus the transient portion. So the steady state is actually right here. That's this I of infinity equals 0 amps. So we get 0 amps plus solving for the coefficients here, this transient portion. So you see it already worked out here, but how did we get that? Well, the first step is to say I at 0 is 2 amps. So we plug in 0 and plug in 0 into this equation, and you get a1 e to the 0, e to the 0 being 1, plus a2 e to the 0, again e to the 0 being 1. So that yields a1 plus a2 is equal to this 2 amps. So we've got one equation, a1 plus a2 is 2. That's not enough for us to figure out what either a1 or a2 is, so we need a second equation. The second equation comes from the derivative of our transient response. So if we go ahead and take the derivative here, that is going to yield, if we know that s1 is negative 2, s2 is negative 3, negative 2 a1 e to the negative 2t minus 3 a2 e to the negative 3t. That's the derivative. So now let's go ahead and plug in 0 into the derivative. We get negative 2a1 minus 3a2. Both of these exponentials go to 0. And we were given that that initial condition for the derivative is 3 amps per second. So negative 2a1 minus 3a2 equals 3. Now we've got two simultaneous equations for a1 and a2. So let's go ahead and write them one on top of the other. a1 plus a2 equals 2. And negative 2a1 minus 3a2 equals 3. And all I'm going to do is multiply the top equation by 2 and add that to the bottom equation. That's going to allow me to get rid of this a1 term. So I'm going to get 2a1 minus 2a1 goes to 0. 2a2 minus 3a2 gives me negative a2. And I'm going to get 4 plus 3 gives me 7. So I get a final expression of negative a2 equals 7. So therefore a2 is negative 7, and you see that right up here. So that is my coefficient a2. Now let's go back to this original equation right here where I just simply have a1 plus a2 equals 2. So that means a1 minus 7 equals 2, so therefore a1 simply equals 9. And that's how we get our final expression for I of t.